Okay. So for the assignment, I have uploaded this document, Guidelines for Writing Assignments, and just outlining, you can say, the formal thing. There will be 4 assignments. You will be using the peer grade systems that I invite you to try, but as asked in the break, it's not mandatory to do that. I mean, if you've done it many times, feel free not to do anything. There's also a little bit, and I've said this also during the lectures, what is a good answer? It all includes that what do you need to get full credit for a particular thing. Of course, whatever numerics that has to be out there has to be correct. But you also have to show that you actually did it. It doesn't make anything more correct that you can copy a textbook. So please don't, and I restate this, please don't spend too much time copying formulas into LaTeX or whatever, because that's not efficient use of your time, nor for those reading it. Do instead make a reference to equation 3.68 or whatever it is. And then just write what you actually did. And another important thing is, if the answer is some numbers, as in maybe up to 20 numbers or something, do include it as a table. The prediction and the confidence intervals for up to 5, 10 observations, it's fine to have that as a table because it's easy to assess if you actually got the right values. Do also make a graph so that you can see, similar to this, that it actually makes sense what you did. I was correcting the other day re-exam assignments, and I looked at a confidence interval where the expected value was outside. Sorry, why hand in something like that? So stuff like that, you see that when you make a plot. You may not always look at it when you just make the table. So for your own sake, do both. Also document which model you used and an estimate. I have too many times seen that you have made what you get to later in the course, an ARMA 2,1 model, period. Yes, you defined the model structure, but you should also present the parameters that you estimated using that model. It's similar to say, I fitted a linear regression model, and not saying anything more. Well, that doesn't tell me, was it a good model or a bad model? So do present the estimated parameters with some measure of uncertainty. For the first assignment, there is one case where you don't have to do that, and that's written explicitly. And the only parameter that you do not need to provide an estimate of the uncertainty for is the sigma estimate, which you may have also have noticed that in the lectures I don't do that either. So that's in a high correlation there. A common question is, well, which function can I use? Can I use whatever method to do this for me? And yes, you can, except that if you are asked directly to do something where you implement the code yourself. But if you pick a function that does something slightly different from what you were expected to do, and you're not sure how to use the particular function to get the expected outcome, well, it's just wrong. You might have known what you wanted to do, but you just did it wrong. So whenever you use a function, make sure that you know what you're doing. So you can say, all the functions that I use are, of course, whitelisted. You just need to use them appropriately. But there are also other functions that you could be used constructively and correct, but I just don't use them for, I don't want to show everything that you can do. They'll take too much time showing code. So there is a balance there, but if you If you know what you're doing, it's perfectly fine. A good compromise is to use, if you do your own stuff, you can use a built-in function as reference to make sure that you actually got the right value. Like I did here, I used the linear model function to just fit the same model. Here it was trivial, but the same idea you can use in other settings. And then you can say, well, if I get different values, is it my code that is wrong, or is it the algorithm that I've used from another function that actually does something different? Then you can say one step deeper. Do include figures. Personally, I'm not a fan of 3D graphics. When I look at it on a screen and I'm not being able to rotate it, it's not so informative. Use some contour plot or something like that. Instead, that's much more informative for the average reader. Or include both if you really, oh, I want that. That's your call. But if you want to communicate some particular values to someone, I mean, how many of you can tell me when I draw, what is the value of that point? I can give it access. It's a free choice, right? Almost. Have quite a large range of coordinates for that point. But if I only did it in 2D, there will be no doubt, right? Regarding code, I find it very helpful whenever I look into assignments to at least every other assignment that I correct. I look into the code to see what did that student actually do. So you read whatever was written and you look at the graphs and it's like, it's very close to be correct, but I'm not quite certain that actually it was done the right way. There's an error, but was it just a small typo, or was it actually a substantial error? Then it's often helpful to go and look into the code. When you peer grade one another, I don't expect you to be able to understand each other's code. But it also means to help each other, do document. Also, whenever you're going back to look at an old assignment, as a minimum in the code, make a comment saying, now I go to question 1.2. Now I go to question 2.3, so forth. Just so that it's easy to figure out where in the code you find things. I suggest that you just have the code as an appendix in the PDF that you will upload. The most common question is, can I work in groups? You can, but you have to hand in individually. So use each other, discuss things, compare results. I recommend that you write your own code. But I mean, just compare, do you get this value? Yes, I got that same value. I mean, all those things help each other out finding mistakes in code. How many of you have been TAs? Do you agree with me when I say that you learn a lot from looking into other people's code? Because you have to kind of see what goes on in there. You also get quite experienced in just finding the simple, stupid mistakes that we all do. I mean, we are only humans. So that's one thing. And I mean, help. I will, in CampusNet, create the assignment. It's already there for the first one. I will send out a message with that so that you can comment on that message. That means whenever you write a comment to that message, I will get an email that someone wrote a comment, and then I will re-comment on that. So for the rest of you who did not write a comment, you can go in and check, did anyone ask something? So whenever you get to a point where you're working on this project, you can go in and see what else was done. Did Lasse actually provide some useful hints? But I prefer to do it that way rather than individual things. Also, I generally say for the last half an hour of the exercise time here, I will be answering questions related to the assignments, but not until 11:30. because I want you to work on the exercises relative to today as well. And I try to choose the exercises and tune the exercises such that if I help you there, it should be easy to make the assignments. So I do not recommend to skip the exercises, that's what I'm saying. And it's not the same looking into a solution as actually solving it yourself, because you lack the mental steps in between. Danish or English is fine. I have preference not to see any other languages. I also made it also for the small test here. Sorry, yes? So in the peer review system, there is a split students into categories. And there's a category for English and for Danish. So at first, I will do this and hope that works out. If there are too few answering in Danish, I may have to do something. I haven't really actually figured out how to do that if that is a problem. But if that is a problem, then I will go in and look at... The usual story is that there is a handful of Danish assignments and the rest are English. If there's only a handful of Danish, I will probably look through those to make sure that the assessment of that is adequate. Because the mixture, the randomization among a small group is not as good as the randomization across a larger group. But that's my task. I do expect to look into quite a few of your assignments, but not to read all of them from end to end. And you can say, when entering, you will be seeing some questions. This is my input signal for that. And I should say that what I did was to create a test case that is assignment 3.1, which you solved last week. To help you out, I mean, in many ways to make an answer to an assignment. The typical way, is that many students use LaTeX, and they produce their graphics, and then they import that and copy the values and blah, blah. That's all fine, but it's also tedious if you have a lot of figures to include to do that manually. There is something called knitter. How many have heard of that? A few. Do you like it? Some do, some don't. The nice thing about knitter, to put it that way, is that you write some LaTeX code, which just looks like LaTeX, and then I can have some R code mixed in between. Some other discussions in LaTeX and some R code. And then when I compile this, what I get is a PDF file where it will... Now, I did not make it nice. You can say that you should hide these things and stuff like that quite easily. But just here to show you, this is you can say the solution to exercise 3.1, where I just, rather than just giving the R code that I gave last week, I mixed it with some LaTeX code. And I didn't spend time to make small, nice dots here, but I mean, take it as what it is, quick and dirty translation into knitter so that you can have your LaTeX structure comments, have your code, and graphics are just included automatically. I don't have to handle anything. You can also take values. I didn't do it here, but you can easily take values and put it into text. So you don't have to write or copy any number. And tables and stuff like that, you could just put that in. But look at the demos on knitter on the website for I mean, all the things you can do. This was just to say it's an easy way. And this was also to make it easy for you to make an answer to upload for the peer review test case here. if you take this here and just, you can say, make it your own, spend half an hour or whatever, and upload it. Then you try knitr, and you can try the system. So the nice thing is that you can reproduce exactly what you did. I mean, how many of you have made a figure, copy it somewhere, and then when you try to remake it, you forgot where the code was? I'll just be honest. So it's not always that easy to reproduce because you change the code in between, and now something is just not the same as it was. This way, when you compile, it runs everything true. If you have something that takes a long time to calculate, it will cache, or you can set it to cache, so it won't redo the calculations. I can say that for the Introduction to Statistics course here at DTU, the entire book that is being used is written in knitr. All graphs, all things are generated on the fly. With a few exceptions, but everything that is plotted in R is made on the fly. So that was just about knitr. Any questions to this? Otherwise, we'll take it later. I'm sure there will be some at some point, but let's take them when they get there. I set this first one here. Let me look at the course overview here. So that it closes the hand-in date on Tuesday next week. The reason for choosing that is then the peer grading opens at the same time, which means that you will have time to look into the system and try to peer grade each other before the lecture next week. And then we will make a short evaluation of that next week. So that's the time schedule. So spend 15 minutes, whatever, alternating my solution to make it your own, add a graph in the beginning, which I didn't do, which I should always do, but you have the data. It's easy to make it. And you can do a lot of tweaks if you like. And you can say the grade should not depend on how nice things look, it's how informative it is. So the easy way, maybe I should just, as a small example, say that the definitions of all the variables up here, if I look at my first part here, if I just want to hide this part up here, I just say this block of R code, echo false. If I recompile, it's gone. So it's very easy to kind of get things out, if you like that. But I mean, there's so many things that you can play with. I don't want to stand here and spend time. But if you just look at knitr, you will find what you need. There are a number of examples. Okay, so now I have two options. And I can still make both. What I wrote in the agenda was to make an R example where I go through some code that could be useful. It's not that you're going to use all of it, but just so that you have some reference code. I can do that now, or I can take the first 10, 11 slides from next week's lecture, because that's what you will be, you can say, answering yet another question in the assignment. So for doing the assignment, right now you can do the first couple of questions, but only the easy part. The next part requires that you kind of go into next week's lecture. So I think that it might be constructive to do the beginning of the next lecture, and then I will at some point, say probably Monday, record, make a link to showing what the code was doing. I will upload the code. I have some comments in there, so maybe it's good enough just as is. You can run it. So for now, I think I will just upload it, and then if you write me, I mean, please explain some things. If more people are asking me to do that, then I will walk through it and make a small video thing with that. But for now, I think if you do not disagree, I will start talking about simple exponential smoothing. Is that okay with everyone? You will need it. There won't be exercises today that are related to that, but okay. So it's section 3.4 regarding exponential smoothing that I'll just get started on. So far, what you've done is to make one model, also what I said today, one model for all the data. I mentioned that next week we'll do local trend models. Now we'll take another approach to do local models, but do local so-called smoothing. And you can say the general appreciation of this is that all models are wrong, but some are useful. And if you only care about, you can say, the near future, say like this, what happened 1,000 years ago doesn't matter anymore. So you want to forget the past and focus on the most recent past. And then make a model that is locally good, not globally good. So the approximation is the same as before. We want to do the Taylor expansion analog, but the most simple thing there is to just estimate a mean value. And that's what we will do. We will just estimate simple mean values. So, how do you do that? You have all your observations, yn minus 1, and down. And one way is to give them exponential weights. So the weight on each observation gets smaller the further you get back in time. Lambda has to be a value less than 1, of course. So you just take lambda to some power, and the power is how many steps backwards in time you go. Then you have an exponential weight that you put. And then you need to define such that the sum of the weights equals to 1. So you just made a weighted average. That's essentially what we're doing. So this constant here should be 1 minus lambda over 1 minus lambda to the n power. When n is large, this here is virtually 0. At least it should be large relative to how close lambda is to 1. But typical values are not so close to 1. So this is basically what you have as an estimator when n is large. 1 minus lambda on this here. But of course we have it the same way as always. I don't want to keep track of all the observations from the past. I want to do something similar to what we did here. I want to update. So how do I do this? If you look at that one there, what do you have? We can separate out the most recent observation, right? And then, similarly to what we did for the F and for the H down here. It's the same thing that we're doing. So, if we look at what we have there, mu hat n equals, let me just do it, 1 minus lambda times, and then I'll just have yn plus lambda yn minus 1 plus dot 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 plus lambda to the n minus 1 power on y1. That's our reference. And then I take the first element out. 1 minus lambda yn plus 1 minus lambda, and then lambda times n minus 1 plus dot 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 plus lambda to the n minus 1 power on y1, like that. If we look at this out here, how do we go from there? We keep the first bit here, 1 minus lambda yn. But if we look at this, can we make it similar to what we have up here as a reference point with a different time lag? What we want to do is to find mu hat n minus 1. We want to make an update of the previous estimate to the most current estimate. So if you look at this up here, you have the 1 minus lambda factor here. Then you have all the y's. You see the sequence here is, of course, 1 shorter than up here. But you have a lambda multiplied on everything that you have up here. So this is the recursion that we're having. You go, when you get a new observation, you take the previous one, multiply by your memory of the past, and add 1 minus the memory times the new observation. So you make a weighted average, essentially, of the previous estimate and the new observation. So if lambda is very close to 1, it has a very small influence on the most recent observation and a lot of weight on the past. And if lambda is very small, well, it's only the most recent observation that matters. And here I'm just rewriting the same thing, but that also means one thing that is not so clear in the book. So I underlined it a little bit more here. We want to use it as a prediction model. When you have this here as a prediction, you do not get any new observations, so you cannot update your prediction. That means that your prediction, however far out in the future you want to predict, you predict the current estimate. It's not always a good estimator. It's a good estimator on a short time horizon. It's not necessarily a good estimator on a long time horizon. But it's just like you're estimating the mean value, and if you're predicting, of course, that's the same value you predict forever. Yes?
That's only for large n, right?
That's only for?
Large n?
Yes.
So you just don't use this if n is small?
Well, what I do in practice is that I start with a clever guess of the first value, and then I just run like this. But that's one of the places where you can actually answer the assignment in a couple of different ways. Either using that I only have 90-some observations and then do the nice calculation, or you can say, well, if I run the filter through like this, starting with an initial value, you're good. What would be, in any case, what would be a sensible choice for the initial value? Yes, use the first observation and start from there. That's an easy one. You can, of course, also optimize what would be the optimal value, but it's an easy one that brings you in the neighborhood of where you want to be going. And this is just a difficult way of writing. This down here, if you're doing Lstep predictions, so if you made an Lstep prediction down here, say 3 steps out in the future, you update that in the same way to get Lstep prediction from yn plus 1. So it's basically, you just run this update here, and then you use the fact that the prediction is always the most recent estimate. And you only update it when you have a new observation. That's the essential bottom line. So for large n, this is what you do. And that's what I expect you to do, so to speak. And the simple exponential smoothing is defined as this sequence doing exactly this up here. You will see sometimes that instead of using lambda, there will be a smoothing constant, alpha, that is 1 minus lambda. So of course you can write alpha there and 1 minus alpha there. It's the same. Just pick one, not both. But it's mostly just to inform you that some places it will be using alpha. Rather than using a forgetting factor, you use a smoothing constant. The game is the same. It's how much information do you keep from the past and how much weight do we put on the most recent observation. Now, the challenge here is how to choose a smoothing constant. What is a good value for alpha? Someone said it earlier today that, well, what if you get an outlier? You're quite sensitive to that. Yes, you are. But that's why we should kind of define some measure. And one measure is to say, you look at the observation minus the prediction Lsteps, conditionally did the Lstep time steps ago. Say let L be 1. So you look at the 1-step predictions, like this, and you sum over all sensible cases. Here's one thing that is a little bit tedious notation-wise. Here I have the sum from t equals 1 to n. Well, then you need a prediction of y1 at time 1 given t minus L. So you need a prediction that was made before the beginning of time of the current estimate. Yeah, I understand that phase. That is not so nice. But if you make the first prediction equal to the first observation, the contribution from that is 0. So you're good. Doesn't make a difference. You could also say, well, it doesn't make sense. Let's start this sum a little bit later. And generally, I think it's also written in a moment, generally, whenever you have n is sufficiently large, you don't care about the performance in the past. You care about the general performance of the system. So it doesn't matter that if you disregard the first few observations. You start with t equals 1, 2, 5, 20, 50. If you got 1,000 observation, you just treat that as a burn-in period. That also means that the approximation here for large n is good. I mean, when we get to a point where 1 minus lambda to the n power is almost equal to 1, that is what where we want to be. So we want to find the alpha or lambda that minimizes this prediction error here, squared prediction error. For the assignment, I wrote that you should disregard the first 20 observations. Then the initialization doesn't matter so much. But keep in mind what it's used for and modify the criteria accordingly. So here I minimize the sum of squared 1-step predictions, for instance, or Lstep prediction. Pick the L that is relevant. Don't just pick one L and use that optimized value for everything else. I'll show you an example. So out at DTU Risø, they're measuring the wind speed and been doing that for ages. 76 meters above ground level, and they measure every 10 minutes. Or at least that's what the data I have. And we want to make forecasts up to 3 hours ahead from now. So generally, the assumption is that, well, we expect that the mean value is not changing. So we expect the wind speed to be the same as it is right now. And that is how the data looks like. And looks quite noisy because there's a lot of observations. But when you zoom in, you can say, as you all know, the wind speed is changing kind of like continuously. So if we do minimize the one-step prediction error, that is, we look at which value of alpha should I use to get the best 10-minute prediction. Then I look here for a number of different alpha values. What is the S of alpha? What is the sum of squared one-step prediction errors? And you see that the minimum you get that when alpha is quite high. So that means that when making a one-step, a 10-minute prediction, what should I do? Using alpha equal to 0.95 is almost the same as forget the past and use the most recent observation. Exactly. So the naive predictor is just to use the previous observation. That works very well on the short-term scale. And I think that's also what we all, from our intuition, that is what we expect. If we go up to 70-minute prediction, you can see that as long as you are in the range here, some say 0.6 to 0.8 as alpha. So you put a lot of weight on the most recent observation, but also some weight on the past. The optimum is around 0.7. So 70% weight on the most recent observation. But now, when you go to longer horizons, the optimum changes a little bit. It never goes down, for this case, to be very small, because there should always be a significant weight on the most current observation, for wind speeds at least. But we see that the longer the horizon, the less weight that you have on the most recent observation. And by intuition, that's also quite good. Now, if we apply this, this is what we get. At first, this looks odd. I will upload the slide later on so you can see it by yourself. So, the black line here are the measurements. Remember that the 10-minute forecast was essentially just using the previous measurement. So when you look at some point in time, might be easy to see with this one, when you want to look at a prediction for what happens at this point in time, I predict the previous observation. In reality, it dropped. But I made a good prediction for the 10-minute prediction. But if I wanted to make a 3-hour prediction here, I actually predicted this value, which was the observation that I had actually before the beginning of this series. So when things are changing as it is right here, the 3-hour prediction is just off. Or it's lagged behind the true signal. So when you want to make a prediction, say at 9 o'clock in the evening, the true value is up there, but we'll predict the value 3 hours before. Of course, you can make more complicated models than this, but just to exemplify. So it also indicates that the one-step prediction, short-term predictions, it seems to work quite well. Also underlying, well, it's a very simple model. It's just a constant. you don't expect things to be constant for a long period of time, but it's okay as an approximation in a short period of time, unless you have something to do with something that doesn't change. But if things doesn't change, it's not so interesting. At least not from my book. So that's, you can say, that's what you should expect to see when you do simple exponential smoothing. You should expect to see something where you shift the signal. And if you look carefully, for the red line, let's just look at down here. That peak here is a little bit more rounded than it is when you look at the observation, because there's this memory. But alpha is only 0.5. So 50% of the weight is on the most recent observation. And then you have, well, 1 minus that, that's also half, times the previous. So you have 25% weight on the one before, and then 12% and so forth backwards in time. So the memory is very short when you have a system like this. Effectively, but we'll get back to that next week, you have 2 observations. You make the average of what corresponds to 2 observations, but you have it with a tail. So, no, that's, sorry. That's where I want to go next week. Yes?
Have you just moved the problem of finding
It comes the other way around. So you define at which interval do you want to make a prediction. And then you figure out which is the best forgetting factor.
okay, but
In,
the time that you think is appropriate?
in this case, but I mean, that's why I wrote previously, you have to consider the context and say, what is the question that is asked in this context? In this case, well, if you want to do predictions for the wind power production, you're up to 3 hours ahead, then you need to have a prediction of the wind speed 3 hours ahead. So it comes from those who kind of deliver the data. They have a request as to what is that you need to do. What do you need to model? And then you can pick the method and you come up with an answer. So here you can say, I just showed you for 10, 70, 130, and 190 minutes. But I mean, it has been done for all the 10-minute intervals in between. So whenever I want to make whenever I get a new observation, I update both the 10, 20, and so forth minute forecast. So I update all of them individually with this system. Generally, I won't ask you to do that. I will just ask you to do, say, 1-step predictions or 4-step prediction or something. But here, I mean, it's optimized for 18 different horizons. When you got it working, it's very easy to redo it. And I just showed you 4 of those, but showing all the others, it doesn't provide more insight. The general insight is that the longer the horizon, the less weight you have on the most recent observation. And then you should expect to see this shift in time patterns when you look at predictions. Other questions? Yes?
At some point, the deviations are very small. If you look at the measurements at 10 minutes and 90 minutes, the deviations are very small as a given point. Accounted for that.
So the up here is performing very well because
Down here to
there? Well, because you're lucky that the wind speed went up and down again. In this case, it's due to luck. It's due to the fact that the measurement 3 hours ahead before was almost identical to the current measurement. So you can say it's luck, or you can say that that's the stochastic process that is driving the wind speed. There is a probability that you'll get back to the same wind speed in 3 hours from now that is right now. Of course there is. I mean, we all know that. And also we can see up here that we have a period of 6 to 8 hours where the wind speed is constant. That happens all the time. And that is also why it makes sense to use the 3-hour forecast from this simple system. The one thing that I haven't said, but I want to just add, maybe have you noticed one thing that I did not do for this simple exponential smoothing? I provided estimates without doing one thing. Yes, there's no measure of uncertainty, or confidence interval, variance, whatever. This is just giving you a value. There is a way to create that, but per definition, the simple exponential smoothing is just giving you a prediction of a value. It's a simple filter. It does not by itself give you any confidence interval. You can construct that by doing what we'll be doing next week and identifying some similarities. But that's also why in the assignment, I will not ask you to do that, but you're welcome to do so if you want to. I call that brownie points. It means that you do get credit, but usually I would say that if you do not do the uncertainty, well, you lose a lot. Here, you can gain a little to make it fair to everyone. Questions? Otherwise, I think it's time for exercises. Yes? Good.